Okay, let us have this nice example here. Now we are going to see the case when we have two strings with one particle. A light elastic string of natural length 2.4 meters and modulus 15 meters, 15 newtons is stretched between 2 points A and B 3 meters apart. So now it's stretched. So now from its nature to 3 it has been stretched apart on a smooth horizontal surface. So first, a particle of mass 1 kilograms is attached to the midpoint of the string. Is pulled 10 centimeters towards B and then released. So let us first see the case before it's then pulled. So case 1, before it's pulled, before it's pulled, this is the case we have. It's attached, this is our horizontal surface, smooth of course. We have end B and we also have A. Now, if we have our particle, it's going to be here. There. So that's our particle we have first. So this one is 4 kilograms. Before it's full, that's the case we are having. That side and also the side. Of course, you're going to be having tension in this string, which I'm going to call T1. I'm also going to be having tension in this string, which I'm calling T2. Of course, this one, the length is going to be L. Let me say L1 up there, but also because it's being stretched, we are going to also have some extension which I'm calling E1 for this string. So even this side, we are going to be having the natural length stopping maybe at that point. Then we have the extension in string 2 to that point. So that's the case. Now we say in equilibrium, if this body is going to move, it means that now our T1 is going to be equal to T2. So those two things are going to be equal. What does it mean? It means that now, you know that from Hooke's law, our tension is always equal to lambda, the extension of natural length. Okay, so this one is going to be equal to now lambda. Let me say lambda, this one is having lambda 1. The expression 1 over L1 equaling lambda 1, expression 2 over L2. So these two are equal. Now, pulled, when it's pulled, and then they are telling us 10 centimeters towards the, where is it? For attached to the midpoint of the string is pulled 10 centimeters. So pulled 10 centimeters towards B. When now we are going towards B, it means that this extension is going to increase because we are pulling towards B. This one is going to increase, while this extension is going to reduce because we are extending the side. So the tensions are going to be different, of course, because we are changing the gymnastics. So now this is the idea when it's pulled. So this is going to be our end A there, and then this is going to be our end B. Now it's pulled towards B. So this is the case we are going to be having when it's pulled towards B. Of course, this one is still our 4 kilogram mass. Before it's being pulled, now this is when it's pulled. So this one is going to be our new tension. Now here I'm going to call it T1 prime. Then the tension in this string is also going to change, so that it's T2 prime. You know that now, remember the natural length of a string and this modulus, they don't change. So this one is going to remain L1 up to a certain point, but because I've pushed it further, the extension is going to change. This extension is going to change by, on E1, I'm going to add on our 10 centimeters are equal to 0.1 meters. So I'm going to add on 0.1 in that direction if I push it there. But this one, the natural length is not going to change. But now, because I'm pushing towards this, the extension is going to reduce. E2 is going to reduce by the distance I'm pushing in this towards that side, in that order. So that's going to be the case. So here is that from here, our T line 1 is going to be, now it's going to be our lambda 1. We assume that this one is having lambda 1. The modulus into now the extension now, which is E1 plus 0.1, which we are calling, so 0.1 more, and say let x be the displacement, or let x be the displacement caused. So now, instead of having E1, I mean 0. Let me put, because let me put this as the displacement caused as x. This is going to be our displacement caused x, then x. When this station are pushing this side, it's going to reduce by that x, and then it's going to reduce also by that x. Okay, so let me now push out this, so that I have this, the whole over L1. So my tip line 2 is going to be lambda 2 into, now E2, the extension, then over L2, as simple as that. Now, from there, what happens? Now, if I resolve horizontally in this direction, I know that always my resultant force is going to be equal to the mass times the acceleration. Now, because the one that showed that the motion, subsequent motion is simple harmonic, it means that now this acceleration is going to be equal to the derivative, second derivative of this displacement that has been caused. Okay, so now if I resolve this direction, so that I have T1, 2 equaling to, okay, minus, this one is opposite, T1 prime equaling to the mass, which is 4, times the acceleration, which I have as now this, because acceleration, whenever it's describing a simple harmonic, acceleration is in that form. So if I put these ones here, so I'll be having my T2 as lambda 2 E2 minus x lambda 2, the whole over L, then minus T1, when I expand there, I have lambda 1, this is 2, L2, this is L1 equaling to 4x double prime. So expanding this, and so we have L2, E2 minus x lambda 2, this is over L2 and this is over L2. I'm separating, then minus lambda 1, A1 over L1, then minus lambda 1, x over L1 equaling to 4x double prime. But now say from here, these two are equal. It means that if I have a negative of this and a positive of this, they are going to cancel out. And so from there, you see, if I factorize out negative x, I'm going to be having L2 over lambda 2 over L2, then lambda 1 over L1 equaling 4x double prime. If I factorize out that negative there, and then from here, you can start my x prime is going to be negative of, if I cross multiply there, I have L1 lambda 2 plus L2 lambda 1, the whole over L2 L1. Remember, we are dividing with this into x, and see that there, that equation is describing a simple harmonic, as you can see if we compare with omega squared x. So now, what do we have? So now our length of these strings Now, from here, let me first show you here, get my cam. Okay, as you can see, this string, I failed to press my string, but I have this. Now, you notice that this string is 2.4 meters. It means that now, from here, we note. From here, I'm going to note lambda 1 is going to be equal to lambda 2 equal to lambda. The modulus of the string, because it was 1 before we attach that particle, we attach it there, it is going to be equal to 215. And now, because these strings were divided into 2, the whole into 2, it means that now our L1 is going to be equal to L2 equal to 2, because this one was 2.4, means that they are 1.2 meters each. So if I substitute there now, my x prime lambda is going to be now negative L1, which is 1.2 times lambda, which is 15, then plus 1.2 times 15, the whole over 4 times 1.2 times 1.2 into x. So here I'm going to get my x prime as, double prime as. So when you simplify there, we are going to be having this as up I'm having 36. What about down? So I'm having 5.76. So here I'm going to have the overall answer as 25/4x. I think you see that if we compare, because they want us to find the speed when the body is at that. So, this was just for calculating. So, here if I compare with this, negative omega squared x, see if I compare this to my omega squared is 25/4, implying that my omega is going to be 5/2, not 4. 5/2, if you get the square root angular speed, 5/2 rad per second. Now, they are telling us that find the seconds, find the distance after, find the speed when the body is away from A. So from A, this is the distance they are giving us. So they are giving us x as 158 centimeters, which is the same as, or this is the same as we divide by 100. If you divide that by 100, you look at this, the sunshine is okay. I think now you see, now when you convert this to meters, this is going to be 1.58 meters. Now from A, now you note that from A, we say that this string has been stretched from here up to here. It's going to be 1.5 meters there. And also, from there up to there, it's going to be 1.5 meters. So in simple terms, they are giving us from the middle, if this is 1.5, in simple terms, they are giving us the displacement as, so this is the length they are giving us from A. So they are giving us this length as L from A. But now, the displacement now from the middle here, if this is 1.5, then 1.5 means 1.5 minus our displacement is going to be 1.58 minus 1.5, which is going to be 0.08. So now, using that idea, I have B squared equal to omega squared into R squared minus the displacement squared. What do we have? So they want us to get the speed. So from here, I'll substitute this as B squared equal to omega squared, which is 2.5 squared into r. What is our displacement? Now, our displacement here, I think you can see the displacement that is going to be constant. Where is the string? Hope remember that this was pulled. Where is it? Where is it? Where is it? Where is it? Was pulled 10 centimeters, meaning that now our amplitude there is going to be our amplitude there. So our R is 0.1 meter. It's the amplitude which was caused when this particle was pulled towards A. So from the center here, because this is our center, when I pull it 0.5 meters, that's the amplitude I'm causing. From the center, then 0.5, I mean 0.10 centimeters. So the amplitude, this is our center. So if I pull it 10 centimeters, it means that that's the distance I'm going to be covering in that displacement. So that becomes our amplitude. So our amplitude is 10 centimeters, which is 0.1 squared, then minus my x, which is 0.08 squared. And from here, my b is going to give 0.1 squared so here I'm getting 0.15 meters per second. So that is my velocity there. Then the period, you know that our period is given by 2 pi over RE, which will be now our over omega, which will be 2 pi over 2.5, which is going to be, your calculator should be here I'm getting T as 2.513 seconds. That's going to be my period. So whenever the particle is pulled, that pull they are causing is always our amplitude, so not that. So then the displacement caused is what we don't know. So whenever they pull it from the here, that what they pull, that distance that it extends is always our amplitude of that particle. So that's how we handle that. Now, other people now, they consider this without anything like a particle. Then they consider that without that particle. But the idea is the same. Anyway, that's it. I wish you well.